Hello, this is our senior design project. We are doing the fishing net buoy lighting with renewable source.
Hi, my name is Celeste Beto, and I'm focusing on power generation and distribution.
My name is Jarrell Coyne and I'm focusing on circuit design.
My name is Anna Villalobos and I'm focusing on power generation and distribution.
My name is Autumn Shulka and I'm focusing on power, circuit design, and sustainability.
And on the right is a list of our team of mentors who are helping us with this project, who have expertise in electrical engineering and marine biology. So the problem is bycatch, which is the incidental capture of a non-targeting species while fishing, and some of these species include endangered species. Once captured in a fisherman's net, they are either harmed or killed. So for our project, we are focusing on the bycatch of sea turtles. To minimize this issue, research conducted by one of our mentors has concluded that having an illuminated net reduced the bycatch by 40% for sea turtles. So our goal is to reduce bycatch that does not decrease the income of fishermen by building an illuminated buoy using green LEDs and powering them through energy harvesting, because the disposable energy sources for the lights are costly and wasteful, such as using glow sticks and batteries. A previous solution has already been developed by our mentors using solar power to power the lights. But there are some disadvantages, such as being fragile, sunlight dependent, and it would need to be recharged once the power was depleted. So therefore, we are trying to come up with another type of power source as an option. So last semester, we researched 3 different methods for harvesting energy. The first is the point absorber method, which uses the wave energy of water. The piezoelectric effect, which uses the kinetic energy in the form of vibrations or shocks, and the tidal turbine method, which uses the kinetic energy of a tidal current stream to rotate a turbine. We are choosing the point absorber method because the piezoelectric effect puts out minimal power, which wouldn't be enough for our design requirements, and the tidal turbine would have biofouling over time, which would cause the turbine to get clogged and not rotate freely the way it should. Some of our design requirements include using 4 green LEDs and having them flash with a 10% duty cycle, a lithium polymer battery, a lifetime of 48 hours, and it should be durable and simple enough for the fishermen to use.
All right, so like Jarrell had mentioned, we are using the point absorber method because it is more realistic and effective. And what the point absorber is, it's a small device that is able to capture the energy of a wave. And as you can see on the right, it can either be floating or submerged. Either way, it's still going to be an energy capturing device. And what we want to do is put our design inside a buoy using electromagnetic induction. And you can see on the left, this is a basic idea on how it works, and how it works for our design. We're going to have a stationary copper coil and a moving magnet going in and out of the coil. And what that does is it creates a change in magnetic flux and therefore inducing current. The movement of the coil and the magnet are relative to each other. And we're going to use a point absorber because it would keep the coil in an upright position, and the magnet would move based on the wave energy. And so this is our circuit design. Over here, we're going to have our magnetic coil and wire with our negative and positive terminals connected to the rest of the circuit. And since the current that is going to be induced is an AC current, we want the rectifier to convert the AC current into DC current. And then we're going to have a capacitor that will be used for storing energy, or we might have a combination of capacitor and also a battery, just in case, just because we're not always going to have a consistent energy source. And next we're going to have, or here we have our LEDs all connected in parallel, and just in case one goes out, we still have the rest of them lighting up. And then we have our current limiting resistors, which will extend the lifetime of our LEDs.
For our design, there are a number of variations, and the variations are determined based on the environment that the buoy will be exposed to. For example, if the conditions are calm water so that there's little wave motion, the ideal design may be to use a sphere magnet because the sphere would experience less friction inside of the tube. a capacitor with a battery, because the battery can be used as an additional energy source if the motion isn't producing enough energy for the LEDs. And we would use more turns in the coil, since the number of turns directly affects the coupling strength between the magnet and the inductor. If the conditions were opposite, so if there were rough seas and a lot of wave motion, our design could support using a disc magnet, just a capacitor, and less turns in the coil, and this makes our design more simple. So after a series of testings, we can determine what variations are most effective for our design. This design has a number of advantages and disadvantages compared to the previous methods that we researched, the piezoelectric and the tidal turbine. The advantages include that the electromagnetic circuit should produce a consistent generation of power as long as the buoy is in the water and moving. The flasher circuit doesn't need to have any extra components because the capacitors should serve that purpose. The design is simple, or is easy, and the construction is simple, and this makes repairs and troubleshooting a lot easier, and the parts are inexpensive. The disadvantages include that there are moving parts in this design, and anytime there are moving parts means that excessive wear and tear may result in damages and replacement of parts. The battery, if it is included in the design, has a limited lifetime, so it may also need to be replaced. And lastly, because there's a large design space, it's difficult to determine the exact conditions and variations that we may need for optimization.
In testing, we will do an induced voltage test where we will have a basic circuit and we will produce a signal on an oscilloscope to see if it will work. And then we will be able to use that to create a better design for a maximum output voltage. And then we will do a complete full circuit test where we will integrate our basic circuit into a full circuit with our LED lights. And there we will be able to see if the LED light up. And then we will do a wave motion test where we will place our design in a waterproof container, and we will see if a simulated wave action will produce the necessary voltage to light up the LEDs. For our locations, we have decided to go to a lake near campus and send our design to Baja California, Mexico, where, with the help of our mentors, to obtain various data. We will adapt and change any necessary changes to accomplish our goals. And we will begin testing March 1st and finish testing by April 1st. And throughout this, we will be completing our senior design projects, which are proposals, presentations, and weekly blog posts. And this will get us prepared for our capstone demonstration date, which is on April 27th. And we will also be continuing doing work for the IEEE student design competition. And in conclusion, we researched 3 methods and decided on the ideal method for our design, which was the point observer method. And we also determined the location for our testing to obtain various data. And finally, we determined the different type of tests to optimize our circuit and for successful results.
Thank you.
Thank you.